Welcome back. So this is lecture 42 in this course on Bayesian modeling. The topic of this lecture is regression modeling using BRMS. Okay. So in the last lecture, we have seen what is regression modeling. Okay. In this lecture, we are going to implement regression modeling using the BRMS package. So just to summarize from the last lecture, you can actually implement any hypothesis which make some assumption about linear effect of something, or let's say non-linear effect of something on a parameter of interest, right? So you can express that assumption within your model, okay? And once you express that assumption within your model, you get basically a relationship between a predictor variable and some parameter of interest, and now you can estimate basically the intercept and slope or whatever other parameters of this relationship between a parameter and a predictor, okay? And that's what we are calling a regression model, okay? So it is very flexible, it is usable in different contexts, right? But it has a lot of applications in psychological sciences. We use these such regression models a lot, right? And the reason is this, because we often manipulate the predictor variables or independent variables to see the effect on the dependent variable, because most of the hypotheses we test in psychological sciences and language sciences are of the sort where we want to see the effect of certain predictor on something else, right? So for example, if we take the classic example of word recognition, where people have to recognize a word on a screen, right? So they need to recognize whether the string written on screen is a meaningful word or not. Okay, so if it is a meaningful word, they would say yes. If it is not a meaningful word, they would say no. Okay, so that takes some time to recognize this word. So somewhere around, let's say, 300 to 600 milliseconds or more, right? So they take some time to recognize this word. Okay, but important thing is this, that we are interested in what are the processes that determine this word recognition latencies in humans, right? So what are the processes that determine that how fast you can recognize a word, right? So for example, a classic theory is this, that if a word is more frequent, or let's say if a word is more familiar, right, then you will recognize it faster compared to a word that is less frequent and has occurred less in your daily uses, right? Which makes sense. So for example, if you see a word like book, you will recognize it very quickly compared to, let's say, you get a more complex word like browser, right? So you will take some time to recognize that word, right? So the frequency of the word will affect how much time do we take to recognize that word. Now that's a hypothesis, okay? How do we test this hypothesis? Regression models are the answer, okay? So let's talk about this particular hypothesis. Can you implement it as a regression model? Well, yes. So all I need is to start with my likelihood assumption, which is about recognition times. So that's a recognition time for ith word comes from, let's say, a normal distribution with mean reaction time mu I for the ith word, for that particular word, and standard deviation sigma. I will not assume a constant average recognition time for all words, because for words the average recognition time should systematically change depending on their frequency. What I'm going to say is that mu I, basically mu, the mean recognition time for a word, is not constant, rather it depends on its frequency. So for highly frequent word, the mu I should be smaller. For less frequent word, mu I should be larger, right? So how do I set up that relationship? I will say mu I is a linear function of frequency of the ith word. Okay. So now I have a regression model for the same thing. It's a simple linear regression model. Okay. If you want to visualize how actually, and you might have done this for frequentist modeling. So let's say in your experiment, you have words with different frequencies. Okay, so between frequencies 1 to 7, you have multiple words, right? And on y-axis, let's say I'm indicating there recognition times, observed recognition times, right? So let's say for word with very low frequency around 1 to, this is actually on GPF scale, so that's why it looks in the scale of 1 to 7. So let's say for low frequency words, the reaction time are somewhere like this. For high frequency words, the reaction time, of course, decreases. Basically, they get faster at recognizing high frequency words. So you get a scatter plot like this. This is a scatter plot. What does it mean? Corresponding to every, basically you are plotting each dot is a stimuli in your experiment, is a word in your experiment, right? And we are indicating its corresponding frequency and corresponding recognition time, right? Now, what we are trying to estimate when we do parameter estimation for this model, we are trying to estimate the best fit regression line in a way. Okay, what do we mean by best fit regression line? Basically, assuming that the relationship between GPF frequencies and recognition times is linear, right? I'm trying to fit a line, a straight line, which best describes this linear relationship between recognition times and frequency. Okay, and when I'm estimating alpha and beta, I'm actually estimating the intercept and slope of this line. So alpha will be slope of this line. So here, this is alpha. Beta will be, sorry, alpha will be intercept of this line. So here is alpha, and beta will be slope of this line. So when I'm estimating these parameters alpha and beta, I'm trying to estimate the best fit straight line that can best describe this linear relationship between RTs and frequency. Okay. Now, of course, this line is not passing through all these points, but that is fine. That is random variation, right? So basically, let us take any frequency, let's say here. So at this frequency, average recognition time we are saying is this. That's what we call mu I. Okay. So given alpha and beta of this line and this particular frequency, this is mu I, average recognition time at this particular frequency. So suppose this frequency is 3.57. Okay, and let's say you have a word with this frequency, and let's say the word is price. Let's say your word with this much frequency, 3.57, and the word is price. Okay, what this equation is telling you, or what this regression fit is telling, so when you basically estimate the model parameters, you will get some value of mu I for this particular word. So the average recognition time for this word price, because you have frequency of this word and you will have value of alpha and beta, so you'll get average recognition time for this word price. And let's say average recognition time comes out to be 600 milliseconds. Okay. Now, although the average recognition time for this word is 600 milliseconds, that does not mean that this is the recognition time you will get every time when people see this word, because there could be still variations depending on the environment, when they read the word, what were the previous words, who is reading the word. So some participants basically can be in general faster, some could be in general slower. So there will be still variation around 600. Okay, so if this 600 is the mean, there would be still variations, right? And that variation is captured by this parameter sigma. Okay, so that's how this model is working. So this line is defined by these parameters alpha and beta, and these variations, fluctuations around this line is given by this parameter sigma. Okay, so this model together will give us basically a scatter plot like this. So for example, if you generate predictions from this model, you can generate a scatter plot like this. Okay, we will see this, we will do this at some point. Okay, so that's how you can define a linear regression model to test the effect of frequency on recognition times in a word recognition task. Okay. Similarly, if you want to do it for word recognition accuracy. So this is for RTs, right? If you want to do the same thing for responses, which could be either 0 or 1, so whether they could correctly recognize the word or not. So that can be given by normal, not normal. The responses are 0, 1, so they should come from Bernoulli distribution with underlying probability of success theta I. So underlying probability of recognizing the word correctly is theta I. And as I discussed earlier, you need to apply some transformation because theta is strictly between 0 and 1. So I can say logit theta I equals to alpha plus beta into frequency I. So what is the use of this transformation? Is that even if alpha and beta have some wild values, let's say very large value or very small values, even then theta I wouldn't go below 0 and above 1, right? So it is constrained between 0 and 1. Okay. So this is how you can define a logistic regression. This is a logistic regression. You can call this one as a simple Gaussian regression. Depending on the likelihood, you can name these regressions, but the underlying idea remains the same. Let us see how do we implement these models in R using BRMS package. Okay. So let's say this is we are taking the same task. This is the actual word recognition time that you are observing. Let us do this for 5,000 words, and let's say it comes from we are testing frequency effect. Let us do it for different frequencies. So let's say, let me first sample frequencies for different words from a uniform distribution. Actually, I'm just trying to generate fake data. In reality, in practice, you would get these frequencies from some corpus. If you're doing a word recognition task, you will get frequencies of words from the corpus. So I'm generating 5,000 frequencies between 1 and 7. Now what I'm going to do, these are frequencies, right? Now I'm going to generate, I will set up first true value of the parameters. So let's say alpha true is 400 milliseconds and beta true is actually 0. Okay, so let's say 5. Maybe 10. Okay, we'll see. We can change it later. And now I will estimate mu I. Okay, so which will be, so this is I'm doing just to generate fake data. So I will generate fake data from the same model so that when we fit the model, we get these true estimates, right? We want to verify whether we are getting these true estimates or not. Alpha plus beta true into frequency. Let us see max mu I. Where is it going? Okay, it's not much. So I think I can increase beta true to 30 milliseconds or so. This is fine now. Okay, so these are now mu i's. Now this is a vector. Mu I is a vector. Now let me generate from a normal distribution. Recognition time in ith trial comes from R norm 1 mu I and sigma true. Sigma true we also need to define here. So let's say sigma true is 60. Okay, it does not give me a vector. I need a vector. Okay, so maybe I can run through a loop. So RT in the ith trial, let me just call it mu, is coming from mu in the ith trial sigma true, right? I can create an empty RT vector. Okay. Now I can create a data frame. So that is basically data frame, frequency equals to frequency, trial ID is 1 2, length of frequency, and RT equals to RT. Okay, so let me do this, and I've stored it in a data frame. So basically I should get now RT as a vector. Okay, so these are the reaction times, and now my data frame has been created. So let me just visualize the data frame. So this is how it looks like: trial ID, frequency of the word in that particular trial, and corresponding recognition time. Okay, so this is fake data. So this is how the data would look like in an actual experiment as well, right? Of course, I can draw a scatter plot to see how it looks like. Okay. So how do I draw a scatter plot? This is my data, GZ plot, aesthetic, x equals to frequency, y equals to RT. Okay, frequency RT. Now I can do Xeon point. Okay, the size equals to 1.2 or so. Okay, so this is how this scatter plot looks like. So with frequency, oh, so there's one mistake we did. So with frequency, RT is increasing right now, but that's not how it happens in reality. So this beta true, if you make it, let's say negative, and the intercept we increase to, let's say, 1000 milliseconds or so. Now this will look correct. Now this is more realistic. Okay? So at low frequency, the reaction time was slow. At high frequency, reaction time is getting faster. That's a scatter plot. Okay. Now we are going to estimate a regression line, a best fit regression line, right? Using regression modeling in Bayesian framework. So how do we do this? We will first define our Bayesian model. So this is our likelihood assumption. We are not assuming log normal. For now, we are assuming normal mu I sigma, where mu I equals to alpha plus beta into frequency in the ith trial. Okay. Now, for prior assumptions, you have alpha parameter. So on alpha, let's say you have prior 1000, 100. On beta, let's say you have prior normal 0 50. On sigma, let's say you have prior normal 0 50. Okay, so these are our prior assumptions. Now let us fit this model using BRMS package. Okay, so load the library BRMS, The data we already have, M1, BRM. Now here we make a change. So rather than writing RT predicted by 1, we write 1 plus frequency, because frequency is the predictor variable here. So we want to predict recognition times using frequency as the predictor. Okay, and that's basically the structure of our linear regression model. You can see here. So RTIs come from normal mu I sigma, where mu I equals to alpha plus beta into frequency. Okay, 1 actually indicates the intercept. This indicates the effect of frequency. So basically, to what extent frequency affects the mean recognition time. So basically, this is about parameter beta. So we are writing intercept parameter here and the beta parameter, which is to what extent frequency affects the average recognition time. Here, of course, the family is Gaussian. Now for priors on intercept, we decided prior of 1,100, which is a reasonable prior. Why we are going towards 1,000? So actually, for intercept here, we are talking about what would be average recognition time for words that have frequency close to 0. So that means for really low frequency words, what would be the recognition time? So it should be very large, so around 1,000. So that's why. Of course, this interpretation will change when we start scaling our predictors, and that's an important thing to do. So by scaling, I mean we change frequency values in such a way that half of the, let's say, some of the words will have negative frequencies, some word will have positive frequencies, such that the word with average frequency, for the word with average frequency, we will define the intercept. So basically, we shift this whole regression line in such a way that intercept can be interpreted as average recognition time for a word with average frequency. Okay, now for parameter beta, normal 0, 50, class equals to B. And now for parameter sigma, it's normal 0, 50, class equals to sigma. For course, iteration 2000, so let us fit this. So just some messages. It's compiling a stand program. It's still a very simple model, so it wouldn't take much time. So now it is started sampling. It will show the progress here. Okay, I think it's already done. It was very fast. So let us see the first, let us inspect the chains. For all 3 parameters, chains are mixing well, so that's not the problem. It shows the posterior distribution here as well, right? But we can check the summary statistics, which is basically 95% credible intervals and other things. That's what we are interested in. Okay, effective sample size are all good, so no problem in there. Now here you would see the coefficients, regression coefficients, right? So this is the estimate for the intercept alpha parameter. This is the estimate for beta parameter, effect of frequency on recognition, on average recognition time. Okay, the estimate for intercept is somewhere between 998 and 1006, right? That's a 95% credible interval. 95% credible interval for the effect of frequency is minus 51 to minus 49. What it tells you is that you can say with 95% certainty that the true effect of frequency lies between minus 51 and minus 49. Okay, and actually this is good, because the true value of beta that we have used to generate this fake data was minus 50. Okay, so the model, the estimates are consistent with that. Similarly here as well, you can see 95% credible interval for sigma is between 58 and 60, 60.56. Okay, but what do we conclude from this about our hypothesis? Recall what was our hypothesis? That high frequency words are recognized faster. So basically, there is an effect of frequency on average recognition times. So that it was our hypothesis. So based on this model output, can you say that there is an effect of frequency on average recognition times? Yes. So based on this output, it seems that the data does indeed support the prediction that as frequency increases, the average recognition times decreases. So basically, word recognition gets faster as frequency increases. Okay. So basically, your data is consistent with the prediction of that hypothesis, but you cannot make a claim that there is evidence for this frequency hypothesis. Okay, you cannot claim that there is evidence for the effect of frequency on recognition times, because when you make a claim, you are implying that this particular regression model that you have used here, okay, that this particular regression model that you have used here, it is doing better than some other model. Okay, but you haven't done that model comparison, right? What if, and you can make that claim about evidence if you compare this existing model against a model of this sort. So let's say mu I equals to alpha plus beta into frequency I, where beta equals to 0. Okay. If you compare this model against this model, and if your model wins, which assumes non-zero value of beta, if your model wins, then you can make a claim that there is some effect of frequency, because a model that assumes that there is an effect of frequency explains your data better than a model that assumes that there is no effect of frequency. Okay, so we are collecting evidence against a model which assumes there is no effect of frequency. So this model comparison is necessary to make a claim about the hypothesis, to make a claim about evidence for the hypothesis. Without model comparison, you cannot say that there is evidence for the effect of frequency. Okay, best you can say based on these estimates is that, well, the effect of frequency seems to be consistently negative. That means the data are consistent with this prediction that as frequency increases, average recognition time decreases, right? So data are consistent with that, because you are getting this consistently the 95% credible interval in the negative range. So the estimate of frequency effect is negative. Okay, that's all you are getting here, right? So you can only make a claim about the true value of the parameter beta, right? So this is the claim about true value of parameter beta, but this does not imply evidence for the effect of frequency. In order to make a claim about evidence, you need to do model comparison. So whether this model is doing better compared to a model that does not assume an effect of frequency, which assumes there is no effect of frequency at all, right? So that's an important thing I wanted to clarify, that of course this 95% credible interval will give you a very good hunch. It would tell you that whether your data is consistent with your hypothesis or not, but you cannot still make a claim about evidence for your model, right? Because that requires model comparison. But this is still useful, and also this is the first step. Without doing this, you won't be able to do model comparison as well, right? So this is the first step that you always do. You estimate model parameters and you visualize, well, how much is the effect of frequency and all that, right? So this is an important step. What if the 95% credible interval is something like -10, from -10 to +10? Okay. In that case, the true value of beta is consistent with a positive effect as well as a negative effect. Then you cannot say that your data is consistent with your hypothesis, right? Then you are in more difficult situation, but you can still do a model comparison to make a claim, right? So this was a simple example where we implemented a Gaussian regression model using BRMS package. Okay. In the next lecture, we will see how to implement a logistic regression model using BRMS, and also Poisson regression model using BRMS, right? So all right, so we will meet in the next lecture and we'll do more practice with the BRMS package for the regression modeling. All right, thank you.